Swayam Prabha. Digital India. Educated India.
So welcome back, students. Yesterday we were discussing about the scale-up criteria which are to be used to keep dynamic similarity at the two scales during scale-up in order to reproduce the results what we get at the lab scale to get reproduced at large scale level. So in that we were discussing that there are various scale-up criteria where yesterday we discussed in detail the power per unit volume scale-up criteria, which is equivalent to considering equivalent mass transfer characteristics at both the scales, and then volumetric mass transfer coefficient, which will be demonstrating equivalent oxygen mass transfer characteristics at both the scales. So now we used these scale-up criteria, and if you remember, we were able to devise how with this scale-up criteria the different operating parameters like the impeller speed, the volumetric gas flow rate in case of a sparged system, and the diameter of the impellers at the two scales, the model and the prototype, which we named it will be correlated. So we had devised various correlations between them. So now the third criteria will be the dimensionless mixing factor. Now this is dependent on many factors like the impeller speed, height of the liquid in the vessel, diameter of the tank, impeller diameter, and the properties of the liquid. So it is to be constant under the turbulent regime where the power number is constant. So dimensionless mixing factor can be considered as constant in the turbulence regime where we know the power number is also constant. So if you see the empirical correlation here given on the slide, the dimensionless factor is a function of the mixing time, the impeller speed, the diameter of the impeller, height of the liquid in the tank, diameter of the tank, and the gravitational constant. Now, as the liquid height being a linear dimension can be related to the diameter of the tank by thumb rules. So, the liquid height can be represented as a function of the diameter of the tank, and further the impeller diameter again can also be related by thumb rules to diameter of the tank. So, effectively this entire correlation can be made in the terms of the impeller speed and the diameter of the impeller and mixing time. So, if we put all these correlations of height in terms of the diameter of the tank and the impeller diameter in terms of diameter of the tank, then we can reduce that same correlation in the form given here. So, if you see I'll name it as equation, okay, on the screen it is equation 8.22. This is directly a screenshot from the book. So, let's call this as equation 1. So, T is the mixing time, N is the impeller speed, and D is the diameter of the tank. Now, we also know that the power number is constant. So, if power number is constant and power per unit volume is also constant, then the correlation which holds true for impeller speed and diameter can be given as n cube d square, which is given here. So, now if you take 18th power of equation 1 shown by me, then you will end up in the equation shown here as 8.2.3, which I'll call it as 2. Further, if the power per unit volume constant in the turbulence region where power number is constant, then n cube d square is also a constant. If we take the fourth power of it, then this is also a constant. So now we can substitute this in equation 2, and the only two variables remain here in the correlation will be the mixing time and the diameter. So now the mixing times at the two scales can be related with the ratio of the diameters of the tank at the two scales. So effectively, this is how power input is related to impeller speed and diameter of the impeller. This is how volume of the tank is related to the diameter of the impeller. Knowing that diameter of the impeller is proportional to diameter of the tank, some scale ratio, and the volumetric gas flow rate is also related to the impeller speed and the diameter of the impeller. Power per unit volume can also be related now. So your equation 1 can then change to, let's call this as equation 3, 2, and this will be 4. So if you apply 1, divide equation 1 by di cube, then you will end up in the correlation 4. Similarly, your third correlation, so where this is Q by V criteria, it is volumetric gas flow rate per unit volume, will give you the fifth correlation, where this is just a function of the impeller speed. So why we have written these correlations? If you notice, this means that most of these quantities, power, volume, volumetric gas flow rate, or power per unit volume, or volumetric gas flow rate per unit volume, which may be useful in scale up, are related to impeller speed and the diameter of the impeller. This means that fixing the diameter of the impeller or the impeller speed can fix all these said quantities. Let's take some examples here. If you see the table here, the pilot scale is at, which we may call as model, is 80 liter. The prototype or the plant scale is 10,000 liters as shown here. So your scale will be the volume ratio. So your linear diameter scale will be, the scale factor is 5. So pilot scale, if we consider the ratio, then at constant P by V, the power will be changing. If you remember how power was related, the power was related as n cube di to the power of 5, and your diameter scale is 5 times. So your constant P by V, if it is the criteria, then it is di square n cube. So they are writing here that the P by V, your power will change 125 times at the plant scale. The power will change by a factor of 3125 if P is 1 there. Then at constant impeller tip speed, which is NDI, the power will change by a factor of 25, and at constant NRE, then your power is getting reduced by 0.2. Then the property of power per unit volume. If at the pilot scale, which is model type, the power per unit volume at constant P by V, obviously it will remain the same. With constant N, which is impeller speed, the power per unit volume changes by 25 folds. At constant impeller tip speed, it will change by 0.2 folds, and at constant NRE, it will change by 0.0016 folds. So if you see similar information as given here we have highlighted few things in red color. Ones which are showing as 1, which means that there is no change in that property because it was held constant at the 2 scales. The which of the property when held constant is bringing about minimum change in the properties on the left hand side, first column. So, let us take for example the numerals which are being highlighted in red here. At constant P by V, it demonstrates how various properties shown in the first column left hand side will be changing at the plant scale level. The power will be changing by a factor of 125. P by V was constant, so it remains the same. The impeller speed by 0.34. The diameter of the impeller 5 folds. The fluid pumping rate of the impeller, which is Q, it is 42.5, and fluid pumping rate per unit volume affects the suspension. So, this is 0.34. Maximum impeller speed will change by 1.7 and Reynolds number will change by 8.5 folds. So, in this case, I find that when we keep constant NRE, the fold change is minimum in most of the properties. So, what are the important considerations? First, we need to identify which properties are important for the optimum operation of the mixing system. Now, this can be mass transfer or pumping capacity or shear rate or any other such factors. Now, the system should be scaled up such that the selected important property can be maintained so as to bring about reproducibility. Although this may result in variation of less important properties during scale up. So, the major difference in the big and the small vessel can be with respect to the mixing time and the shear rates. Now, for homogeneous reactions, power per unit volume can be used as a scale up criteria. Cells are uniformly suspended, it can be called as a homogeneous mixture. For effective scale up of gas liquid contactors where two phase interactions are important, gas liquid interactions, then KLA can be used as a scale up criteria. The fermenters that are not usually operated for optimum gas liquid mass transfer due to shear sensitivity of the cells. So, let us see the correlation once again. For constant power per unit volume, the correlation between the impeller speeds and the diameters is shown here. Then for constant tip velocity, which was NDI, this will be the correlation, which is very simple. Then constant dimensionless mixing factor will give us the correlation here. If you remember, equation 1 shown here was a correlation for dimensionless mixing factor. So, if apart from the constant mixing factor, if we can imply constant power input per unit volume at both the scales, then further your correlation 3 can be reduced to only correlation relating the mixing time with the diameters. So, what are the basic steps which one must follow during scale up? First, investigate the process in the laboratory, select the strain, the suitable raw materials and their composition. Optimize the process conditions like pH, temperature, etc. Measure the properties like volumetric gas flow rate, the impeller speed, various yield parameters, yield of biomass with respect to substrate, yield of oxygen, biomass with respect to oxygen consumed, yield of product with respect to biomass, or yield of product with respect to substrate consumed. So, various yield parameters and the dimensions of the fermenter. Now, vary Q, which is volumetric gas flow rate or the pumping rate, impeller speed, and study its effect on the performance of the reactor. Further, determine the broth properties, the liquid properties, density, viscosity, diffusivity, and other parameters of the liquid. Calculate the VVM, which is Q by V, the volumetric gas flow rate per unit volume. So, aeration number, which is nothing but Q by NDI cube, shear rate, and Reynolds number. So, with the help of the properties measured, we can calculate the gas flow rate in terms of VVM, aeration number, shear rate, and Reynolds number. Now, predict power input per unit volume, volumetric mass transfer coefficient. Now, determine which parameter influences the yield and productivity most. This parameter should then be kept constant on both scales. Now, going to the plant scale reactor calculations, choose the volume required based on the yield and required capacity. Calculate the dimensions based on geometrical similarity. Based on the chosen scale-up criteria, determine the airflow rate, the rotational speed of the impeller at the large scale or the prototype, and calculate the power consumption and other parameters.